incredibly, this is a parametric function. The pixel as input and has roughly 50 million parameters. When you run it, and you can run it in moderns today on a phone, just a simple cell phone without even internet, like basically on the battery, it is going to do something like 15 billion calculation in a flip of a second, like roughly around 100, 200 milliseconds, and get you the result. So that's the power of deep learning. Why is deep learning interesting is because you do not have to figure out what features are important for your problem. Contrary to machine learning, where you have to do a lot of work on features, here on a vision type problem and others, basically the system figures out the right features by itself, which is very powerful. So an implication of this, which is pretty cool, is basically recognizing diseases just looking at a retina eye scan. So this is an eye scan and if you look at the blood vessels, how the blood vessels are shaped, how thick they are, how geographically positioned they are, you can actually predict incredible things. You can predict the age of a person, more or less 3 years. You can predict the gender. You can even predict if that person is going to be likely a cardiovascular risk or not in the next 5 years. So this is an interesting point, because in the past, doctors would not be able to do this. There is no doctor that saw a correlation between blood vessels in the eye and on the retina and basically multiple diseases or fundamental information about who you are. So that's the power of modern deep learning systems. They can go beyond what humans have thought about and capture correlations which we never thought existed. This is work done by the Google Brain team, and which is now rolled out in basically healthcare units in the US and others. There's a lot of potential for AI and healthcare. So that is deep learning. And remember, we said initially that there were two technologies, reinforcement learning and deep learning. So we're going to look at the second one now, which is reinforcement learning. So what is reinforcement learning? Is this idea that, like a baby, I'm gonna try things and see what works and what doesn't. This is an interesting concept, because if you look in the case of Atari games over here, this is a game of Breakout that made DeepMind famous. So the idea is only pixels and a score, and just with that, the system figures out how to do smart things, which is like go hit all the bricks on top. So that was the breakthrough from DeepMind in 2013, 2014. And since then we've had multiple breakthroughs. You can get a humanoid to discover locomotion just by giving it rewards every time it reaches point B starting from point A. The game of chess and go over here. But the concept is always the same. There is a reward, and the system is going to try all sorts of random stuff first, see what works, what doesn't, and it's going to slightly increase the probability of the paths that lead to a good reward against those that don't. And incredibly, if you take the same kind of paradigm, you can get to very advanced stuff, which is like, how do I manipulate a cube to find the letter I'm looking for? Robotic hand manipulation is a very difficult problem, and we're making like significant progress with a combination of deep learning and reinforcement learning. So, to tell you how far we can go with these systems, this is learning end-to-end. So in this example from Google and DeepMind, you actually go from pixels, this is OpenStreetMap, you go from literally pixels to deciding which way you should go in the city. So it's literally learning to drive in the city or to orient itself in the city just visually. Like yourself, if you start to know a city pretty well in Dubai or anywhere else, after a while you don't need a GPS, you know where you're going. This is the kind of system. Same thing with another recent breakthrough, which is Capture the Flag. It's a DeepMind game that DeepMind has solved. Incredibly, you can even create complex common behaviors between teams just starting from pixels. Like, what's impressive here is you did not tell the system anything. You're just rewarding it if, in the case of like going from point A to point B, you reached destination, and that's it. And those systems can do this. So this is learning end to end. There's also this concept that these systems can be deployed really at scale. A recent breakthrough from OpenAI, actually it's just a few weeks old, was to, in the game of Dota 2, was to be basically, play as a team of 5 against the world champions and beat them. Then they took over the whole internet for a weekend. I see some people have followed this, it's pretty cool. to see like if the system could be beaten, and the answer is yes, it can in a few cases, but still it's a 99.3 or 0.5% win rate against all the whole world. So that shows you how powerful these systems are. To give you an idea, I mean, we talked a lot about the game of chess and Go because it was such a fundamental breakthrough. After all, AI was invented, by Alan Turing and others in the 1940s and 50s, in particular, to solve the game of chess. But to tell you how quickly things are going, now we're talking about 1,000 actions. In chess, you only have roughly 35 positions you can play at any point. In Go, in the order of 200. Now we're talking about 1,000 actions. We're talking about a state space like the board of the game, if you want. In chess, you could summarize it with 70 dimensions. In a complex game like Dota, you need 20,000 dimensions. And now it plays in real time. It doesn't play turn by turn. All this happened in a year and a half since DeepMind basically released its results on game of chess and Go. So it's incredible at which speed it goes, but it's incredible the scale at which modern compute jobs can go, because here we're talking about 128,000 CPU cores, hundreds of GPU, and a system that effectively learns the equivalent of 900 years of playing every day. So this is how big these systems go, and incredibly, the more power, the more scale, the better the results. So that shows you what's possible. This is today considered the state of the art, is the latest result from DeepMind about StarCraft 2. And again, look at the exponential growth here. We started from backgammon, which was solved in the 80s, to chess, which in its first version against Kasparov was solved in 1997, even if arguably there was a lot of brute force in the method, to now Go, a few years ago, to now StarCraft 2. Look, Go, for example, is 10 to the power 170 possible game configurations. So we're talking about the same number of atoms as in the known universe. But then in StarCraft 2, we're much bigger than that. So that shows you the kind of exponential growth that powers these systems. And that takes me really to the key point I want to make in this presentation. It's like, why should you be AI first? It's because AI is a triple exponential that's moving really, really fast. So it's a triple exponential of data, hardware, and also algorithms. This is not just the machines being more powerful. The algorithms themselves are much, much smarter than a few years ago, and they keep getting smarter. So if we look in detail about these components, data is more important than algorithms. Why can I say this? It's because if you look at the history of AI breakthroughs, every time an algorithm was invented, nothing happened. What happened was, like, the breakthrough happened very quickly after the data set on which the AI system could work was made available. For example, if you take, for example, hidden Markov chains in the 80s, nothing happened, but then as soon as this spoken text database from the Wall Street Journal came in, speech recognition became a reality. Google Translate, same story in 2005. As soon as 1.8 trillion data points became available, bam, you had a revolution in translation. And same thing with vision. ImageNet was what made vision possible. Vision was actually, technically speaking, available since the late 80s, early 90s. So data and exponential growth in data, but particularly organized data, is critical for AI success, and it grows exponentially. So when it comes to hardware, it's the same story. How many people have heard about Moore's law here? Okay, many people, almost all the audience. That's good. It's this concept that compute power doubles every 2 years. Actually, in modern machine learning jobs, compute power deployed for machine learning actually doubles every 3 months and a half. So it's absolutely crazy, and it's been the case since 2012. And it is set to continue, because some people are going to say, yeah, but Moore's law, we're reaching the limits, it's not going to continue. I mean, when I was a student some time ago, I was reading also like, yeah, Moore's law is going to stop. The reality is, even if you reach the limits of integrated circuits, another technology will come, such as quantum machine learning, and keep going. So what's the fundamental limit? The fundamental limit is actually much bigger. It's 10 to the order 33 compared to where we are. This is coming from physicists at MIT that calculated those limits based on what we know about quantum phenomena. So taken into context, that's 200 more years of doubling every 2 years. So, you know, don't worry, like compute power is going to keep growing at a crazy, crazy rate. So that's the double part. We said it's a triple exponential, data, compute. And on the algorithms themselves, incredibly, actually, the number of research papers doubles every 2 years and kind of fits a Moore's law, ironically speaking. There has never been in history so many high-quality researchers focusing on machine learning. What that means is that we have an exponential growth of small tweaks, but lots of small tweaks can get you a long way, as we have seen with all the progress recently. So the algorithms themselves are continuing to increase, and here I'm not even saying like massive breakthroughs such as deep learning. Just in deep learning and reinforcement learning itself, all those small tweaks add up, and that means that those systems can do wonders as time passes, and the number of people who focus on them is increasing, and that's not going to stop anytime soon. So that is the triple exponential. And when I look at, that is where we are today, but tomorrow what's interesting is that AI itself is going to accelerate each one of those components. So this is actually AI for basically data. So it's possible now to create modern art paintings so good that you could not recognize them from like a true artist. So it passes the Turing test in computer science parlance. Same thing with manga, same thing with music. And I mean, look at those faces. It's actually pretty incredible to believe that those are not real. Actually, you know, sometimes I ask people like, try to find the real one, and many people will say it's the old man over there, because the wrinkles, the facial expressions, like you would have a hard time believing this was generated by an AI system, but yet it was generated by an AI system. This is pretty much state of the art. Recent results from Karim in 2019. So think about it. I'm drawing something like 500 random numbers, and I put them into a deterministic function. It has 500 million parameters, but at the end of the day it gives me each pixel of this. And almost magically, all those pixels collected together create meaning, which is kind of hard to believe. I mean, I'm a practitioner in this industry, and I still find those results fascinating, and expect more. In the future, AI will generate high-quality videos, which will be indistinguishable from the real thing. So why is this speeding up AI? Because, as we said, data is critical for AI. And in many industrial-type jobs now, you can actually improve the performance of your machine learning system with what we call augmented data. For example, Waymo in self-driving is actually capable of taking video footage of real cars driving and real drivers, and maybe take 10 hours of that and make that 1,000 hours by varying conditions, by creating trees, by making it winter time, while there it was summertime, and others. This is important because that means that your data can actually go much, much further. And that is how AI boosts data. So AI, you know, as I said, triple exponential. On the data part, AI is going to accelerate data. Same thing on hardware. Very interestingly, now you have some of the world-leading teams that are studying how AI can be used to build better integrated circuits or better allocation when you have to work on multiple machines. So this is a result from Google AI, where they showed that a system just playing reinforcement learning on the game that, hey, I want to increase efficiency, can actually beat the experts. So the fundamental insight behind all those is that human intuition comes from experience, yet there is a limit to how much experience a given person, even an expert, can have in a lifetime. So systems that learn by themselves, they can go way beyond that, here 20% faster, but recent results would be even bigger. And finally, on the question of machine learning itself, designing the machine learning model, incredibly, artificial intelligence can give you better results than the experts. So in this example from Google Brain and Jeff Dean's team, actually for vision, it is possible to design automated machine learning systems that are going to create a child machine learning system here. So this is the master AI, which is building up the child AI, if you want, and trying multiple combinations, trying to find the right one. And to give you a sense of how quickly these things are moving, when Google published this in late 2017, they needed 800 GPUs running for almost a month. So everybody said, hey, this is too big, this is only Google who can do this. But then something like a year later, it runs on one GPU in less than a day. And today, actually, you can have those tools for yourself because they are available in Google Cloud AutoML, and I'll be talking more about that. So it's actually incredible. Look at the speed up. We're talking about 1000x speed up in this something like a year. So that shows you how far we can go. So to give you a sense of the results, if I put here in axis the number of the compute budget, like how much multiplication and addition I can do versus for vision, for example, like the accuracy that I'm getting in vision, you can see that as I increase the scale of my model, I get better accuracy, but it's kind of like plateaus in a sort of logarithmic way. And this is literally years of effort by the whole machine learning community. Some very famous models out there. So what happens if I try to automate machine learning? Incredibly, I get better results. So both for small constrained models, like models that would run, for example, on a mobile, I get a higher accuracy model with a smaller compute budget. So this is pretty important. And the same thing on large models as well. So the good news is this type of breakthrough technologies actually are available. So this is to get you a sense of what to expect in the future. And by the way, this is not just from me, this is from Jeff Dean, the head of Google AI. So he actually wrote this in 2017, and AI progresses so quickly that when I look at some of those queries, I'm like, hey, in some cases, we're almost there, or if not there yet. Describe this video in Spanish. You could do that now. Find me documents related to reinforcement learning for robotics and summarize them. Pretty much there. Fetch me a cup of tea from the kitchen. Robotics is getting there. Which of these eye images show symptoms of diabetic retinopathy? We saw that example early on. So, interestingly, this was 2017, it was considered like, wow, this is unachievable, blah, blah. And today, you know, in 2019, we're almost there in all of those. This is a very cool example, which came in recently. This is due to, from OpenAI. Basically, it's a natural language understanding system. On that. And what's incredible, so I said that's a hard one as an assignment, and the system is capable of writing all this text, and if you read this text, actually it has a pretty cool meaning. It's saying like, no, recycling is bad, because to start with we should think about what we put in the package before we think about recycling it. Like let's save matter first, etc., etc. It's incredible. Like just a year ago this was considered science fiction, yet we are there. Actually, this model, which is called GPT-2, OpenAI thought it was so powerful that decided not to release it to the general public. It has 1.5 billion parameters, and it trained roughly on all of Reddit Q&A. So imagine in the future what can happen if you have a system like this with bigger number of parameters training on a big part of the whole internet, for example. We know that scale makes those models better and better, but this is qualitatively different. If you look at what we had a few years ago to this, it's really qualitatively different. So that's where we are in terms of AI today and tomorrow. So how can you make AI a reality for yourself and your organization? So it really takes 5 steps, and they're really not hard. First step is Google Cloud and cloud-based APIs. You have a vision API, speech API, translation, video intelligence. All those work already. And the cool news is they can be available to you for free. So up to a certain amount of usage, these are actually for free. So really, like, there's no excuse not to start using AI within your organization, because the tools are there and it costs literally zero. All what it costs is a bit of curiosity maybe and a bit of time, and that's it. So this exists today. Incredibly, I told you about AutoML. AutoML is actually available today. So that means that if you have a particular data set, you're going to be able to get the essence of that dataset or squeeze the value out of that dataset better than any point in the past, because the model that AutoML will deliver to you will be adapted to your data rather than having been designed by other people for other objectives. So this is pretty important and pretty transformational. The MIT Technology Review actually listed it as one of the 10 breakthroughs of last year. It is a game changer, and again, it's available on Google Cloud today. If you want to go beyond, there is this TensorFlow, basically, which is available. TensorFlow is like the Android for machine learning and AI. It is by far the most widely used platform in the world today. Developed by Google Brain to start, but totally open source now. So I had this question earlier. Actually, you can use TensorFlow completely free, like you'd own Google nothing. Any product you build on top of it is your intellectual property. So it's a no-brainer, and Google put all its resources behind it to offer this product to the general public, and which is also used internally at Google very extensively. So to give you an idea, what's interesting about TensorFlow is the fact that you can productize very easily. So you can go in production deployment very easily with TensorFlow, because machine learning and AI is not just about training a model. This is actually a starting point. The hard part is about how do you build a robust production-ready infrastructure, and that's not easy. So you have lots of tools such as TensorFlow Extended, which help you along your machine learning pipeline if you want. So step number 3, hardware. So Google Cloud GPU is becoming a game changer in machine learning. So if you have an internet connection, you will have access to high performance computing at very often a very attractive price. So that is also available today. So you set yourself up, you try API for a start, or AutoML. If you want them to be more advanced and own the IP, you can build your own TensorFlow product, and ultimately, train it on dedicated hardware. When it comes to team learning, a lot of information is available already. So, as I was saying earlier, the difficulty is not to find information, is to find the right information. There is actually a lot of noise. So I've collected for you things that I think, some of the resources which I think are really high quality. In particular, highly recommend the Deep Learning book from Goodfellow. It's a great one. For more advanced people who want to dig into reinforcement learning, the Sutton book is a must. And you have plenty of classes online. You have machine learning crash course with Google, Udacity, Coursera, and the like. Andrew Ng did a keynote a bit earlier. He talked about the work that you're doing on Coursera and deeplearning.ai. And how do you know if you're good or not in AI? The best way is actually to compete with other teams. So there is a Kaggle Day happening today at AI Everything. Next Kaggle event, register your team, because nothing beats competing with others to get a good sense of where you are today. At InstaDeep, for example, this is how we benchmark our capabilities compared to other companies and how competitive we are. So after all this, data. So data is kind of like, AI is in many ways is a hammer looking for nails, and data are the nails. So data is super important. So I'm going to quickly walk you through an example of how you would build a visual AI tool. So let's say you want to recognize all those products, Pringles, all sorts of products that you would find in the supermarket. You have no model, you have no data, you're just starting. So what does it really take for you to build that kind of visual AI model? It takes you actually roughly 300 original picks for each product. So you will recognize this Pringles box. It's going to take you something like 300 photos. 300 photos is really nothing. You could get those in an afternoon with your team, or even a few hours. So what happens next is this notion of invariance. So a Pringles box remains a Pringles box even if you turn it around, even if you change the background, put a background here, or turn it around, or zoom, or get out. So you're going to use those data invariances. For example, from one original photo, I could synthetically manufacture 20 augmented photos from my Pringles box. So if I have 300 pictures, that means that now I have 6,000 pictures to train my model. And that is roughly the order of magnitude at which you would train a high-quality visual AI system. So now comes the time to train the whole model. Sometimes these things can be very expensive in terms of compute power. So very interestingly, there's this concept which is called transfer learning. So remember what we were talking about in vision when we started. Vision, when you start, it does some basic stuff. It's towards the end, it builds up a higher level understanding. Well, it's this idea. Actually, if I want to recognize my Pringles box, I'm going to only go and change the end, the classification part, and retrain that. All the first modules there are like generic vision models. Actually, if I use a trained model on something else, it will still work because it's really recognizing like basic intensities and edges in photos. So the cool thing is you have lots of available models out there on the internet. At Google, for example, you can go to Tensorflow Hub, you will find many pre-trained models. So effectively, it's like somebody wrote you a check for free computing, because you're going to take a model which is already trained and you're just going to modify it slightly towards the objective you're looking for, and it will work. Interestingly, this is not just about vision. It's also about, for example, natural language understanding. Google released recently a super powerful model of natural language understanding called BERT for bidirectional transformers. So that model, actually, you just need to retrain it on your particular problem or your particular questions and answer, and it will deliver very high performance in natural language understanding, powering your bots, for example. So the AI community is incredibly open, and thanks to like wise leaders such as Google and Facebook AI and OpenAI and others, you have so many tools which are available for you to basically get started and can actually get a headway, like a head start for no cost, really. So that's the concept of transfer learning. Finally, on data, there are other tricks you can do. For example, with AI at the edge, you could run a visual AI system for a year without electricity and without internet. Basically, just on a battery. The battery could hold for a year at today's quality hardware. So that means that you can accumulate tremendous amount of information about the real world. The real world is full of information. The reason why some people are better than others is just that they are smarter and more clever about how they capture the data. Let me give you a very clear example. Tesla, and you have a Tesla demo there, a Tesla car there. Tesla in 2012 had very few cars on the road, maybe in the order of a few hundreds, and was not considered even as a serious car maker. Today, Tesla has the best data asset in history and on the whole automotive segment. Why? Because they had the vision to put up sensors and cameras on all their cars, so every time you drive a Tesla, you're accumulating data, actually, which is fed to Tesla. So it's an AI at the edge, actually, work that they're doing up there. So acquiring data is as much a question of willpower as it is of means. Like, don't believe that, hey, I cannot do it. Actually, it's very possible to accumulate data. You just need a very wise strategy to get there. Same thing with decentralized data gathering. This is probably the next revolution. Federated learning as well. It's this idea that, hey, I'm going to train on each cell phone of my customer base, for example. Their photos or their data is private, so I do not want to upload that to the cloud. But you don't need to upload it to the cloud. You can train the model directly on the phone, and what you're uploading after that is an average model out of everybody's phone. So your privacy is guaranteed, but at the same time, the learning and like the advanced machine learning system has been fed. So this is the kind of paradigm shifts that are happening today, and stay tuned on those. You will see a lot more on that in the future. So to give you an idea, I mean, this is the kind of example of what a few years ago would require still a very expensive infrastructure if we have internet. Let's wait a few seconds. This is a visual AI example. The point I'm making here, and it doesn't matter if you don't have the video, I will share to you the slides later. The point we're making here is that in these days, you can actually have those just on the edge without internet, and that's